Before we start, we can review a couple things, review some notation. So recall, and let me focus this a little bit. Before we start, we're going to look at some notation. And remember, this symbol means for all. And this backward E means there exists and so we'll be using that a lot from here on. And also, there's an important theorem that comes up a lot when we're doing proofs. It's called the Archimedean property. And it says for all x in R, and again, R is the real numbers, there exists a natural number. And again, this symbol means natural numbers. And those are, remember, counting numbers like 1, 2, 3, etc. And also remember this symbol, this means in. So for all numbers x, like all x in the real numbers, there exists a natural number such that n is greater than x. So for example, you can like just pick a number, say 2022, then there exists a natural number greater than that. And let me do 20, let me just make it more specific, say 25, 22.3. Then there is a natural number, and you could pick many, you have many different options. Then 3,000 is greater than 25, 22.3. And you could have picked even, or you could have just picked 25, 23 is greater than 25, 22.3. You have a lot of options. But the point is that this Archimedean property says that for any real number you pick, there's going to be a natural number. You're going to always find a natural number bigger than that. And that seems pretty obvious, but we often have to apply it when we do proofs and stuff. So keep that in mind. So again, that's the Archimedean property. And also later, we're going to be doing proofs and theorems. And remember, when working with theorems, to prove a theorem is true, or statement is true, we must prove it in general terms. We can't just go through and pick a bunch of values and show what works for a whole bunch of numbers. Therefore, that proves it. We have to prove it in general terms, because sometimes something might work for hundreds, thousands, even millions of examples, but then there might be one time out there where it doesn't work. Now, to prove a theorem is not true, all you need is one counterexample. So you don't have to prove anything in general. If you want to show that something's not true, all you have to do is find one, just one example that does not work. Now we're going to take a look at elementary number theory. And we start with a definition. An integer n is prime. Excuse me. I want to start with an integer n is even. Integer n is even if and only if n is equal to 2 times k for some integer k. So an integer is even if you can write it as 2 times some integer. And integer is odd if and only if that integer is equal to 2 times an integer plus 1. So that's definition of odd and even integers. If it's even, it's good. You can write it as 2 times another integer. If it's odd, you can write it as 2 times another integer plus 1. And another definition, an integer n is prime if and only if n is greater than 1 and it is divisible only by 1 and itself. And you probably know some of the prime numbers off the top of your head. Some common ones are 3, 5, 7. So like, for example, 3 can be divided by only by 1 in itself. 5 can only be divided by 1 in itself. And actually, technically, 2 is a prime number. You wouldn't think so. But 2 is a prime number by our definition because it can be divided only by 1 in itself. And another way to say this is n is prime. And I'll use notation this time. These symbols here mean if and only if. Before I wrote if and only if. I'm going to use a symbol now. If and only if for all positive numbers, I should say for all positive integers, R and S, if n is equal to R times S, then either R equal 1, S equal n, or R equal n, S equal 1. So n is prime if only if for all positive integers R and F, R and S. If you have this relationship n equals R times S, the only way that can happen is if R is 1 and S is n, or R is n and S is 1. That's again, this is another way of saying the number is prime. And another definition, kind of the alternative to prime numbers, are the composite numbers. N is composite. Once again, if and only if there exist positive integers R and S such that n equal R times S before, and R is between 1 and n, and S is between 1 and n. So that's the definition of a composite. Again, a composite number is not prime. And so notice this definition, how it's written. It's composite if there are two numbers R and S such that this number is equal to R times S, and R is greater than 1, but less than this number n, and S is greater than 1 and less than that number n. Then it's composite. Let's go ahead and go through some proofs here. And let's do this example. Prove that the sum of 3 odd integers is odd. And so we'll say put proof. You'd say proof or solution. Now, whenever you want to prove something like this, it's very important to start with let. So let, and usually let will be whatever you're starting with here. So like, for example, let M, N, L be integers. And now we want them odd integers. So we could say let M and L be integers such that now we want them to be odd. So we're starting with 3 odd integers. So let's call M equal to 2R plus 1. Remember, that's the definition of an odd integer. It has to be of the form 2 times an integer plus 1. And we'll do the same thing with N. And we'll use maybe a different one here, 2S plus 1. And then L, let me call that maybe 2T plus 1. Where R, S, and T are integers. So it's very important. Always start with let. Now I could have skipped this first part here. I could have just said let M equals 2R plus 1, N equal 2S plus 1, L equal 2T plus 1, where R, S, and T are integers. So I could start with that, but always have to start with a let, and then kind of stating what you're starting with. So notice, because in our problem here, we have to prove that the sum of 3 odd integers is odd, so we have to start with 3 odd integers. So always start with let. So start with let, and then put the stuff and conclude with what you're trying to prove. So now again, we're starting with those 3 integers, and we want the sum of those 3. So it's going to be M plus N plus L. And so I'm just going to add them together. So I'm just adding together these numbers up here. And now we want to prove that this sum is going to be odd. So let's start rearranging things a little bit. Let me put the letters together. So I'm going to put the letters together, and then I'm going to add up the 3 ones. And again, we want to prove that this is an odd number. So we have to kind of rearrange it. Remember, to prove that it's odd, we have to show that we can get it into a form like this, where 2 equals 2 times some integer plus 1. So let's work with this. Let me rewrite this a little bit. Let me put a 2 over here like this. Now I'm going to factor out a 2. Like this. And notice we have, remember, the sum of integers is an integer. So this group right here has to be an integer because each of these individual terms are integers. So this is an integer. And so we have 2 times an integer plus 1. That's the definition of an odd number. So therefore, this is odd. So notice in order to prove this, we started out with what we had to start with. We wanted the sum of three odd integers. So we let M, L, and K be the three odd integers. And we had to put them in the form of odd. And then we want to show that the result was odd. So we added them together and got them in the form 2 times integer plus 1, which is the odd. Now let's take a look at another one here. The sum of any two even integers is even. So prove this. You can say solution or proof, however it is. So once again, we want to show that the sum of any two even integers is even. So once again, we have to start with let m equal 2 times r. Again, that's an even number, and we need two of them. So let's pick another one. N equals 2 times s, where r and s are integers. And again, so we always have to start with whatever we have. You can always say let. And then we have to prove that the sum of these is even. So let's go add them together. Excuse me, m plus n equals 2r plus 2s. And we can factor that. R plus s. Once again, since these are integers, the sum is going to be integers. So this is an integer. So remember the definition of an even number. It's going to be 2 times an integer. So this is even. So once again, notice how we did the proof. We want to show the sum of two even integers is even. So we have to start with two even integers and then show that the result is even. And those are formal proofs. Now we're not always going to have to do them formally, but this is how you would do the formal proofs. And let me do maybe one more. Suppose m and n are integers, is 12m cubed plus, excuse me, times n squared. Is this even or odd? Let me write that a little bit better. 12m cubed n squared, even or odd? Now, this isn't really a proof. They're kind of just asking us, a question. So we don't have to do that let type thing. Although it may be good to get used to doing that when it's appropriate. So like here, we'll just say let m and n be integers. It doesn't really specify what type of integers, if they're even or odd. And now let's put this together. Then And again, this isn't a formal proof because it just asks us a question. So then if we have something like this, cubed and squared, and let's see what kind of form we can put this into. Let's notice we can factor out a 2. So this is 2 times 6 m cubed n squared. And the product of integers is an integer. So this is an integer. N is, m is. Of course, 6 is obviously an integer. And so this is an integer. So what we have here is 2 times an integer again. So this is going to be even. Notice this was not a formal proof because they asked a question. Usually we only prove things if a statement is made or a theorem is made. And that'll be the same with the next question. It's not, we're not going to have a formal proof. So like this one here, once again, just asking us a question. If A, B are integers, is 14A plus 16B plus 1 odd or even? And solution. Once again, I'm going to start with a let. Again, this is not formal. Let A, B be integers. And then we have 14A plus 16B plus 1. Let's see. Once again, we can factor out a 2 out of here, can't we? This is going to be 7A plus 8B plus 1. And this looks like an integer here. Remember, products and sums of integers are integers, and these are all integers, so that's an integer. So we have 2 times an integer plus 1, so this has to be odd. Remember, that's the definition of an odd. So this is odd. And we'll take a look at one more short proof here. Prove that the following is not true. There is a positive integer n such that n squared plus 3n plus 2 is prime. Now, this is a little bit different, and we're proving that that this theorem is not true. And so it says that the proof they're following, there is a positive integer n such that this is prime. Now, again, we can't test every possible n, but we can do this in general terms. And one way to do that is, so if we're looking at this, so if we want to say so the statement says there is a positive number such that this is prime. To disprove it, we can prove that this can never be prime. So we want to show can never be prime for any n. And of course, how do we do that? We can show that this is a composite number. So remember, if something's prime, it can't be composite. Something composite can't be prime. So we'll show that this is a composite number. So notice that we can factor this, can't we? This is going to be, can be factored into n plus 1, n plus 2. Simple as that. And so we have an integer here. And we have an integer here. And so this is a composite number. And notice we didn't pick a particular n. Notice that we only used, we just used a general n. So this means the fact that we use a general n, that means that no matter what n we pick, we're going to get a composite number. So therefore, there cannot be a number such that this is prime, because we're always going to get a composite number no matter what n we put in. So now we're going to talk about rational and irrational numbers. Start with the definition. A real number is rational if and only if it can be expressed as a quotient of two integers with a non-zero denominator. And the real number that is not rational is irrational. And we can state all this formally. Formally, we can say if R is a real number, then R is rational if and only if there exists integers A and B such that R is equal to A divided by B and B is not 0. So mainly if R is a real number, that's rational if and only if there's two integers such that R is equal to the quotient of those two and B is not 0. So just some examples. Take a look at these. Five, 319. So let's take a look at each of these. Now notice 5 is rational because you can write it as 5 over 1. Again, rational, where the word sort of comes from, it has ratio in it. It can be expressed as a ratio of two numbers. And now this is 3 over 19 is obviously rational. And what about this number here? Notice you could actually write that as 5667 over 10,000. So that's rational. And actually, when you have something repeated like this, that's usually going to be irrational. And actually, 0 can be written as 0 over 1, or you could write it as 0 over 56, or 0 over almost any other integer you want. So this is rational. So rational, 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 irrational, rational. And there's another important property that you probably have used many times, but never really thought about it. It's called the zero product property. If neither of two real numbers is 0, then their product is not 0. And then, of course, if the product is 0, if product, going the other way, if product of two real numbers is 0, at least one of the numbers must be 0. And that's why we can solve certain things such as this. You know, you've done this in basic algebra a lot. If you want to find the solution of a quadratic, remember, you might factor it and set it equal to 0 if you want to find the solution. And remember, you know, because we're working with real numbers, that for this to be 0, this has to be 0, or this has to be 0. One of these two must be 0 for this to equal 0. And this is not true with other kind of system, not true in all algebraic systems. For example, you could have, like, if you've had matrices before, you could have something like this. Notice this is not 0, obviously. That's not 0, but let's multiply these together. We're going to have -1 plus 1. Excuse me, I need another -1 right here. So multiply these through, -1 plus 1. And then over here, 1 minus 1. Down here, -1 plus 1. And 1 minus 1. So 0, 0, 0, 0, like that. So here, neither of these were the 0 matrix, but yet when we multiplied them together, we got the 0 matrix. So in some other system, this 0 product property is not true, but in real numbers it is. And that's why we can do things like that, and it comes into play a lot. And probably, as we saw a minute ago, and this is actually a theorem, that every integer is a rational number. Because as we saw with 5, we can always rate that integer over 1. And let's look at another theorem here. The sum of any two rational numbers is rational. And let's prove that. Like I said, now we're going to do it formally. So again, start with what you have. You're talking about two rational numbers. You want to look at the sum of those. So we're going to set up two rational numbers. Let me call one of them R. Let R equal A over B. And S equal C over D, where A, B, C, D are integers. So again, we're trying to prove that the sum of any two rational numbers is rational. So we have to start with two rational numbers. Again, we always start with let, and then say what you're going to be starting with. Let this be a rational and this be a rational, where these are integers. And then we want to show that the sum of these is a rational. So start with these, then add them together. So we need to show that this sum is going to be rational. So let's find a common denominator. Let's multiply this numerator and denominator by D. And let's multiply this numerator and denominator by b. Now we have a common denominator. We can add them. This is going to be AD plus BC, BD. And of course, AD, those are integers. BC are integers. The product of integers are integers. So that's an integer and that's an integer. Then we add those two. The sum has to be, the sum of two integers is an integer. So this is an integer. And again, here, these are both integers. So the product of two integers is an integer. So we have a quotient of two integers. So this has to be rational. So again, notice how we did the proof. We started out with what we start out with in the statement. We're going to say let R and S be two rationals. Again, write them as rationals. What the definition of rational mean. You didn't have to use A, B, C, D. You didn't even have to use R and F, but it would be if you have to start with these two forms where these are all integers. Then we have to talk about their sum, so add them together. And we want to show that that sum is rational. And so we got that. Next we want to talk about is divisibility. If N and D are integers, then N is divisible by D if and only if N equals D times some integer and D is not equal to 0. If N and D are integers, then N is divisible by D if and only if N equals D times some integer. Now, there are other ways of saying this. This can be said in other ways. We can say N is a multiple of D. That'd be another way to say it's divisible. There's another way to say that N is divisible by D by saying N is a multiple of D. Or we could say D is a factor of N. Or we can say D is a divisor of N. Or they sometimes say D divides N. Now for some notation, D with a straight up, a vertical line, N is red, D divides N. And then we can say D divides N if and only if there exists an integer and let's call it K, say K, such that N equal D times K and D is not equal to 0. And so then there's more notation, other notation. We can say D where there's a slash that vertical line and is red. D does not divide. And furthermore, when you have something like this, implies N over D is not an integer. And so, for example, you could say something like this. You could say 2 divides 8 because you can divide 2 into 8 evenly. Or because this implies that 8 is equal to 2 times some K, which of course in this case is 4. Or another case here, you can say 3 does not divide 10. It's not a factor of 10. You can't write 10 as 3 times something. And there's some common theorems. Some of these are pretty obvious. For all integers, A and B, if A and B are positive, and A divides B, then obviously A has to be less or equal to B. That's pretty obvious. You know, if one number is going to divide another one, it has to be smaller or at least equal to it. And another theorem. The only divisors of 1 are 1 and -1. And let's go through some examples. If A and B are integers, is 12A minus 6B divisible by 3? Of course, all you have to do is show that it's a factor. The 3 is a factor of this, so we can start with what we have here. And notice we can factor 3 out of both of these. So 3 for A minus 2B, like that. And of course, this is what it means to be divisible. If you can write write this number as 3 times an integer. Obviously, this is an integer. And so the answer is yes, it is divisible by 3. Another example, if A and B are integers. And actually, to tell you the truth, A and B really don't even have to be integers for this to be true, because this would still be divisible. So if A and B are integers, is 15AB plus 10A divisible by 5? And once again, see if we can factor out of 5. And we can. So we can write this as 5 times another number here. And we're going to go through a few more theorems here. And this is called the transitivity of divisibility. For all integers A, B, C, if A divides B, and B divides C, then A divides C. So if A divides B, B divides C, then A divides C. And another theorem, divisibility by prime. Any integer n greater than 1 is divisible by a prime number. And another very important theorem, if a and b are positive integers, and if a divides b and b divides a, so if they divide each other, if a divides b and b divides a, then that forces a to be equal to b. So these are all important theorems. And now we'll do what's called the fundamental theorem of arithmetic. For all n greater than 1, there exists a positive integer k along with distinct, that should say distinct. Let me read that a little bit better. Distinct prime numbers. P1, P2, PK, and positive integers. E1, E2, EK, such that n equal P1 to the E1, P2 to the E2, P3 to the E3, EK to the EK, where the primes are kind of increasing, PK. So you can write any number n in this form. Basically, you can write any any integer n in this form where n is greater than 1. You can always write it as a product of primes to a power. And this form right here is called the standard factored form. And let's go through some examples here. Let's rate each of these in standard factored form. Let's write 130 that way. Let's write 96 that way. 44. 100. And 3,300. So sometimes it might make a few steps. Remember, we have to write this as a product of primes. And so sometimes you just start factoring it. What does this look like? Maybe 2 times 65. And then just keep factoring until you have only primes over here. And this factors in the 5 times 13. And there we have it here. We've got 130 written as a product of only primes. 2, 5, and 13 are all primes. So let's do the same thing over here. Like I say something, just kind of keep factoring it. And so 2 times 48, then 48 can be written, what is 6 times 8? And then 6 can be written as what, 2 times 3? And 8 can be written as 2 times 2 times 2, huh? So I think we have only primes now, don't we? And then finally put all the common primes together to power. So let's see, we have 1, 2, 3, 4, 5 2s. 2 to the 5th, and then 3 like that. Or you can write 3 to the 1st power if you want to put the power on. So again, only primes. Now, of course, the exponents don't have to be prime, though in this case they are, but they don't have to be prime. And down here, once again, with this is 2 times 22, and 22 is 2 times 11. I guess those are all primes. And 2 times 11. So we've written it as a product of prime. Once again, the exponent doesn't have to be prime. And 100 can be written as 4 times 25. And 4 is 2 times 2. 5 is 5 times 5. That's 2 squared, 5 squared. Finally, 3,300 can be written as 33 times 100. And let's see, 33 can be written as 3 times 11. 100, let's see, can be written, what, 5 times 20. And 3, 11. 20 can be written as 4 times 5. And 4 can be written as 2 times 2. And so let's gather our numbers together. Again, always put them though in ascending form just to make it look nice. So we have 2 2s, 2 squared. And then we have 1 3. We have 2 5s. And 1 11. Let me put that. You don't have to put the powers, of course, if they're to the first power, but. So all of these are written in standard factored forms. Remember, the final form has to have only primes.